Hello everyone, welcome back to my channel. In this video, I'm going to discuss NCERT Class 12 Physics, Chapter 3, Current Electricity. Now let us first try to understand what is electric current. Electric current, denoted by I. Okay. Electric current is defined as rate of flow of charge. Rate of flow of charge. Alright. So the electric current is equal to the charge flow Q upon time. Anything divided by time is known as rate. Rate means dividing by time, okay? So electric current is defined as the rate of flow of charge. So I is equal to charge flown upon time. Anything divided by time is known as rate. Rate means dividing by time. Alright. Now we have average current, I average. Average current is given by delta Q upon delta T. Now, if this is a conductor, consider a cross-section of the conductor. Consider a cross-section of the conductor. Now, if charge del Q flows through this section of the conductor in time delta T, then the average current will be given by delta Q upon delta T. Are you getting that? Okay, if this is a conductor, consider any cross-section of the conductor. If charge delta Q flows through this section in time delta T, then the average current will be given by delta Q upon delta T. And the instantaneous current, I instantaneous. The instantaneous current is given by dq upon dt. Okay? If a very small amount of current dq flows in a very small time interval dt, then the instantaneous current will be given by dq upon dt. Okay? So that is all about electric current. And let us see what is the unit of electric current, SI unit of electric current. Electric current means charge flow, okay, upon time. Charge, SI unit of charge is coulomb, SI unit of time is second. So coulomb per second is known as ampere. So the SI unit of electric current is ampere. Current is said to be 1 ampere if 1 coulomb of charge flows through a conductor or through any section of the wire in 1 second. Then the current is said to be 1 ampere. If 1 coulomb of charge flows through any section of the wire in 1 second, then the current is said to be 1 ampere. Now, classical story of electric current. Classical story of electric current. From this story, we'll try to understand what is drift velocity. Drift velocity. Now, in electrostatics, we have learned that the electric field inside a conductor is always zero. Alright? In electrostatics, we have learned that the electric field inside a conductor is always zero. Now, if an external electric field is applied, E external. If an external electric field is applied, then what happens? We know that a conductor, okay, has lots of electrons present. Electrons are negatively charged, and we know that negative charges always moves in a direction opposite to the electric field. As the electrons are negatively charged, the electrons will move in a direction opposite to that of this electric field. Okay, so the electrons accumulates at this end of the conductor. Now this end of the conductor has now lack of electrons because the electrons have already moved towards this end. So the positive charges appears on the other end of this conductor. Okay, so when an external electric field is applied, then induced charges appears on the opposite ends of the conductor. Due to these induced charges, an electric field is set up inside this conductor known as the induced electric field, and the electric field, okay, it's in a direction from positive to negative. So this is the direction of the induced electric field. So due to this induced charges, induced electric field is set up inside the conductor, and this induced electric field is in a direction opposite to that of the external electric field, but equal in magnitude. That means the induced electric field and external electric field will cancel out each other, and the net electric field inside the conductor will be 0. So E induced will be equal and opposite to that of the external electric field. In that case, the induced electric field plus the external electric field will be equal to 0. That means the net electric field inside the conductor is again 0. Alright? Okay. You can note this down. Now, as the net electric field inside the conductor is 0, then what happens to the electrons present in the conductor? Are they still in motion? Are they still moving? Or are they at rest? What do you say? They are still in motion. Okay, they are still in continuous motion, and it is due to the thermal energy of the conductor. Okay, even though the net electric field inside the conductor is 0, the electrons are still moving. Okay, and that motion of the electrons is due to the thermal energy of the conductor. Now, as a large number of electrons are present, okay, so as the electrons move, they continuously suffer collision with the positive ions of the conductor, and hence the net flow of the electrons, okay, in any particular direction is 0. So even though the net external electric field inside the conductor is 0, the electrons are still in continuous motion, okay, and their motion is due to the thermal energy of the conductor. So the velocity with which the electrons are moving, okay, is known as the thermal velocity of the electrons. Now, as the large number of electrons are present and their motion, okay, is random, so they suffer collision with the positive ions of the conductor, and the net flow of electrons in any particular direction is 0. That means their average thermal velocity, the average thermal velocity of the free electrons is 0. So U average thermal velocity, okay, of the electrons in the conductor is 0. So if U1, U2, and so on up to UN, okay, are the thermal velocities of n number of electrons, then the average thermal velocity U1 plus U2 and so on up to UN divided by n is equal to 0. So the average thermal velocity of the electrons in the conductor is 0 because of their continuous random motion. Alright? Now, if you connect the conductor to a battery, suppose battery has potential V, let's say that the battery has potential V. So if you connect the conductor to a battery, then a potential is set up across the two ends of the conductor, and hence an external electric field is set up. Is it okay? Hence an external electric field is set up. Now, this time the electrons, okay, the electrons are negatively charged particles, and we know that negative charge moves in a direction opposite to that of the external electric field, right? So the electrons, they move towards this end of the conductor, that is opposite to that of the external electric field, and the positive charges moves towards this end of the conductor. Okay? Now this time, these charges, they don't accumulate. They don't accumulate at the two ends of the conductor. Why? Because the conductor is being connected to a wire. So the negative charges flows through this section of the wire, and the positive charges flows through this section of the wire. So there will be no accumulation of charges across the two ends of the conductor. So since there is no accumulation of charges, the induced electric field inside the conductor will decrease, and it will be approximately equal to 0 now. Alright? So the net electric field inside the conductor will not be 0 because the induced electric field inside the conductor is 0. So the net electric field inside the conductor will not be 0. So this external electric field will also be developed inside the conductor. See, do not think that the battery offers electrons to the conductor. Do not think that way. Okay, the battery always drives the electrons. They always keeps the electrons in motion. They keeps on driving the electrons. Okay, they never offer electrons to the conductor, but they always drives the conductor. They always drives the electrons. Okay, yeah, they mix the electrons in continuous motion. Now, this time the induced electric field inside the conductor will be 0, so the net electric field inside the conductor will not be 0. So the electric field that is produced inside the conductor will be this external electric field. This external electric field will be developed inside the conductor. Now, due to this external electric field, the electrons experiences a force, right? The electrons experiences a force, and they move in a direction opposite to that of the external electric field, right? Because electrons are negatively charged. Negative charges, they move opposite to the electric field. So the electrons experiences a force, and according to Newton's, the electrons experiences that force, and we know that electric field is given by force experienced per unit charge. So in that case, your F will be Q times E, right? So under the influence of this external electric field, the electrons, they experiences a force, And that force experienced by the electron will be given by minus E. Charge of an electron is minus E times the electric field E. So the electrons experiences this much force, okay, this much force, and they move in a direction opposite to that of the external electric field. Now, as the electrons experiences a force, they will accelerate and hence their velocity will increase. Okay? Yes. But this increase in velocity lasts only for a very short time, because as the electrons accelerates, again they will suffer collision with the positive ions of the conductor. Okay? And hence the electrons, they will thus start afresh with their initial thermal velocity. Are you getting that? Yes. So that short time interval for which the electrons accelerates before they suffer collision with the positive ions of the conductor is known as relaxation time. Okay? Yes. So if V1 is the velocity of the first electron, okay, before it suffers collision with the positive ions of the conductor, then from the equation of motion we know that V1 will be equal to U1 plus A tau 1, where tau 1 is the relaxation time for the first electron. Similarly, for the second electron, V2 will be given by U2 plus A tau 2. Similarly, V3 will be given by U3 plus A tau 3, and so on. Velocity of the nth electron, Vn, will be given by Un plus A tau n, where tau n is the relaxation time for the nth electron. So the average of these velocities, okay, before the electrons suffer collision with the positive ions of the conductor is known as drift velocity. The average of these velocities is known as drift velocity. So drift velocity means the average velocity with which the electrons, okay, move before they suffer collision with the positive ions of the conductor is known as drift velocity. Now, if V1, V2, V3 and so on up to Vn are the velocities, okay, of n number of electrons before suffering collision with the positive ions of the conductor, then their average velocity V1 plus V2 and so on up to Vn upon n, their average velocity will be given by, now V1 means U1 plus A tau 1, V2 means U2 plus A tau 2, and so on up to Vn means Un plus A tau n divided by n. Now we know that we are going to rearrange this. So this average of these velocities, right? Average of these velocities is known as your drift velocity, and I'm going to denote it by Vd. Drift velocity. Average of these velocities is known as drift velocity, denoted by Vd. And if we rearrange this, then U1 plus U2 and so on up to Un, okay? Plus we can take A common, taking acceleration common, tau 1 plus tau 2 and so on up to tau n divided by n. Rearranging, we have your Vd is equal to U1 plus U2 and so on up to Un upon n plus tau 1 plus tau 2 and so on up to tau n upon n. Here U1 plus U2 and so on up to Un by n is your average thermal velocity, And we have seen that the average thermal velocity of the electrons is 0. So average thermal velocity of the electrons is 0 plus A, and then tau 1 plus tau 2 up to tau n upon n is known as your average relaxation time. Average relaxation time, we will denote it by tau. So this is equal to your acceleration. Okay, according to Newton's second law, we know that force is equal to mass into acceleration, where m is the mass of the electron. Then your acceleration will be given by force upon mass. So your acceleration will be given by, what is your force? Minus E times E upon m. So your acceleration will be minus E, charge of an electron, into E upon m into tau. So this is the required expression for the drift velocity of the electrons in the conductor. So I repeat, drift velocity means the average velocity with which the electrons gets drifted under the influence of the external electric field is known as drift velocity. So now we'll derive a relation between drift velocity and electric current. Relation between drift velocity and electric current. Now, let us consider a conductor of length L. Let us consider a conductor of length L and area of cross-section A. Okay. Consider a conductor of length L, area of cross-section A. Then the volume of the conductor. Volume of the conductor will be given by area of cross-section times L. Okay, volume of the conductor will be given by AL, where A is the area of cross-section and L is the length of the conductor. Let's say that N is the density of the electrons of the conductor. Density of the electrons means number of electrons per unit volume. Okay, if N is the density of the electrons means if N is the number of electrons per unit volume. That means in 1 unit volume, N number of electrons are present. Then for volume AL, okay, if the volume of the conductor is AL, then the number of electrons will be N times AL. Okay, so total number of electrons present, the total number of electrons in the conductor of volume AL, in the conductor of volume AL will be given by N times the volume of the conductor. Are you getting me? N is the density of the electrons, means number of electrons per unit volume. 1 unit volume means N electrons. This much volume means this much number of electrons will be present. Okay, number of electrons present in the conductor of volume AL will be given by NAL. If E is the charge of each electron, then the total charge of all the electrons in this conductor will be given by E times the number of electrons present in the conductor, right? So total charge total charge of all the electrons, of all the electrons in the conductor, will be given by the number of electron times E. Alright, E is the charge of one electron, and your conductor has this much electrons, so the total charge of all the free electrons in the conductor will be number of the electrons times charge of each electron. Now, if this conductor is connected to a battery, say of potential V, okay, suppose if this conductor is connected to a battery, then the potential will be set up across the two ends of the conductor, and hence an electric field will be set up across this conductor. Now, due to the action of this electric field, applied electric field, the electrons gets drifted towards the positive end of the conductor, right? With velocity, say Vd, where Vd is the drift velocity. So under the influence of this applied external electric field, the electrons will get drifted and they will move with velocity Vd towards the positive end of the conductor. Now, if t is the time taken by the electron, to cross the length L of the conductor, okay, if t is the time taken by the conductor to cross the length L of the conductor, then t will be given by distance upon speed, displacement upon velocity. So L is the displacement, Vd is your velocity. Time is given by displacement upon velocity. Here the total charge of all the electrons in the conductor, let me denote by Q. Total charge of all the electrons in the conductor. Now, from definition of electric current is defined as charge flown upon time, rate of flow of charge, Q upon T, right? Okay. Electric current is defined as the rate of flow of charge, so Q upon T, charge flown upon time. Now your charge is total charge of all the electrons in the conductor, Q is equal to NAL times E upon time. Your time is L upon Vd. Here LL cancels out, so we have I is equal to NAE Vd, which is the required expression for the relationship between drift velocity and electric current. Is it alright? Are we clear with you? Yes, please note this relation down.